field. And so all I need to do is then add a little twist of, if the current's changing, then my magnetic field, the magnetic field is changing, therefore the magnetic flux is changing, and that has implications that we will get to in chapter 32. Any questions about this before we take another look at Ampere's law? Ampere's law we talked about, actually when we derived the formula that I just erased, when we had the infinite line here, and we found that the magnetic field was mu naught I over, or the strength of it, over 2 pi r. When we derived that, at that point I did a little hand wave and I said, the generalization is this always works where it's mu naught I, or the magnetic field times whatever the length of the line is, or actually more formally, if I have any closed loop, B dot dl is equal to mu naught times the current that's enclosed. That's not the current that's running through the loop. That is, if I have a loop here, it is the current that is basically encircled by my loop. So when I want to go through a more complex problem than what we've dealt with before, where we just have a single line of current, but also we need to address something that I jumped over before. I made a passing reference to it, I think, a couple times. But if we look at Kirchhoff's junction rule, where we talked about at any junction, current flowing in equals the current flowing out. Matter of fact, at any point, current flowing in equals the current flowing out. But that seems to ignore what happens with a parallel plate capacitor. Because if I have a current flowing in, I do have a current flowing off the other plate. But there's this gap here, which we completely ignored. And so we need to somehow address the fact that if I have a current coming into the plate, it feels like there should be something leaving this plate. And that is the contribution of Maxwell to Ampere's law. And the implications are enormous. All right. All right, so I have a wire here with current equal to 3 amperes, and the current's equal to 3 amperes, and current density is uniform. Refresh your memory. The current density is basically current divided by area. So if it's uniform, it doesn't matter which section I take, I'm going to have the same amount of current per unit area. And what I want to know is, what is the magnetic field this distance away? Let's see, I need to get 2 specs here. I need to tell you how big the wire is. And so let's make it unrealistic. Let's make it 2 meter radius wire. So a wire that's basically a little bit taller than I am. So diameter more than twice me. And let's make this 1.5 meters. What is the magnetic field at that distance? First off, let's deal with the direction. What is the direction? All right, so the dots there are representing the current coming out of the board. So what is the direction of the magnetic field along that dotted line I just drew?
It says currents coming out of the board, right?
Yep.
What's coming out?
So
Counterclockwise.
we got a counterclockwise and
Counterclockwise.
Okay.
Yeah, counterclockwise.
looks like people are, with the hand gesture, are doing it right. So current's coming out, magnetic field's curling around like that, so magnetic field is going around in this direction. I'm going to use Ampere's law, because otherwise it would have been really silly for me to start out talking about Ampere's law. So the magnetic field times that length there. Well, first off, because of the uniform distribution, there's no reason to think the magnetic field would be different at this spot than it is at this spot, strength of the magnetic field. That it would be the same magnetic field strength all the way around. So my integral of B dot dl, since the magnetic field is, the strength is uniform, in other words, it does not depend upon where I am, it can come out. Also, when you're doing this line integral, you basically use the right-hand rule to know which way you're supposed to go around the loop. Current's coming out, and so I'm going to do my line integral here in a counterclockwise direction. So at any point right here, dl would be something like that. B is in the exact same direction. It should have been a regular vector symbol. In other words, they're parallel to each other, so this just becomes d times the circumference there. 2 pi times 1.5. And that should be equal to mu naught times the encircled current. How much current is actually going through that loop? Book does refer to it as an Amperian loop. I'm sure I've referred to it as a Gaussian loop, and might still again. Feel free to correct me if you want to, or just run with it. Gaussian loop, Amperian loop, I will use interchangeably. Well, I know my current density is the same regardless, so I know that the current through the whole loop divided by the area of the whole loop, it's got to be the current of my partial loop, T for partial, or my area of my partial, I guess, wire. So that's 3 over the area, and what's the formula for area? Oh, yeah, there's a pi in it.
Pi r squared.
Yeah, so that's pi times 2 squared. It's got to be equal to the current going in the smaller loop there, divided by pi over 1.5 squared. And so my current that is enclosed, my partial current, is just equal to 3, the whole current, times this fraction of 1.5 squared over 2 squared. Which is 3/4, 9/16, 27/16. So that would put it at 11/16. So I'm breaking down your forces. What is it really? Yeah, you're right.
You're on to something with 11/16.
Yeah, let's try to remember what 11/16 is. So, well, 11/8, 1.625.
Six, 8, 7, 5.
somewhere I did a boneheaded mistake. Anyway. Units, not that we really care at this point, but units,
Amperes.
yep, it's a current. So that's gonna be equal to mu naught times 1.6875 amperes. And so my magnetic field, the strength, my magnetic field strength, I should say, is gonna be equal to 4 pi times 10 to the negative 7 times my current, 1.6875 amperes, divided by 2 pi times 1.5 meters. And this is Tesla meters per ampere. Oh, yeah, it has to be Tesla meters per ampere.
Got 2.25.
Double counted somewhere. Oh.
Yeah, I got 2.25.
Times 10 to the negative 7th
Tesla.
units?
Tesla.
Oh, sorry, you just said that, didn't you? Yeah, sorry about that. And I know what you're thinking again. You're looking at that going, man, that's just incredible. Physics is just so incredible, just probably the best subject ever. Can you beat it though? Oh yeah, I can beat that. Any questions before I make it even more exciting? I originally was gonna also throw in a non-uniform current density, but I don't think it brings that level of excitement that you're used to. Let's address Ampere's law and the parallel plate and how we deal with it. I have some sort of DC power supply. I've got a parallel plate, capacitor. Now what happens when I actually make the connection here? So let's assume that there's some switch that is here, the plate is discharged, everything is just, we're starting fresh, and suddenly we make that connection. What happens sort of physically here?
The spark.
Assume that there's no spark. What happens as far as the parallel plates are concerned, or the capacitor is concerned?
The electrons start building up on it.
Which side? Given my drawing.
On the right side.
Okay, so I got an electron that shows up here, and that electron gets chased off of this one. So we got these charges building up. I know that capacitance is equal to the charge over the potential difference between the plates. And that's the definition of capacitance. So from that, I know that the charge on the plate ultimately will just be C delta V. Now, if the parallel, in the ideal parallel plate capacitor, I get these buildup of charges, I got this voltage in between them, and I got this electric field between them. And since the electric field is uniform in between there, again, that the electric field between the plates the magnitude of that electric field is, I guess I should say, magnitude of that electric field times the distance between them is equal to the voltage. So I can make that substitution, so I get CED. And again, that E is the magnitude of the electric field, is not the energy. The capacitance, it's a parallel plate capacitor. Obviously, this is a pseudo derivation because I'm using a very specific capacitor here. But the capacitance is also epsilon naught A over D times ED. My D's cancel out, and I'm left with epsilon naught A times E. Then what is A times E?
Electric flux.
So I have the charge that is on the plates is equal to epsilon naught sine times my electric flux. You can also think about this, not sort of, but also think about it as I create a Gaussian surface around the plate. And so I know that electric flux is going to be equal to the enclosed charge divided by epsilon sub naught. Then you pretty much get to the same place. So if we're talking about current, I have current that's coming up onto this thing. I have a current that is flowing because I have, in theory, positive charges flowing onto the left plate or negative charges flowing onto the right plate. And the rate at which those charges get on there is equal to my current. So my current is equal to the rate at which the charges build up, which is just equal to epsilon sub naught times the time derivative of my electric flux. Now, I have labeled this as I, but it's not the same type of current that we've been dealing with. The current we've been dealing with has been dealing with a charge actually moving, but there is no charge that's moving in between the plates. There's a charge moving on the one plate and off the other plate, but not in between the plates. We have no charge. And so this type of current is called displacement current. So what Maxwell did is he took Ampere's law, which we have in pieces right there, and he said B dot dl is equal to mu naught times current plus this displacement current. He just tacked on an extra current in there. Traditionally written distributed out, so this is equal to mu naught I plus mu naught I sub d. And then go ahead and substitute that in. You get mu naught I plus the sub zero, mu naught epsilon sub naught d phi sub e dt. We now have Ampere's law with Maxwell's addition. Sometimes Maxwell's correction. So now we can really use, if we consider this new thing as a current just as legitimate as the other current, Kirchhoff's rule now seems to apply to all cases. Maxwell takes this little piece and runs with it, but there's one more piece that we need in order to actually finish it. So that is the subject of the next little bit. Are there any questions? All right, so that's chapter 31, which is one of the reasons there's no master set on it. So magnetic field from a long straight wire we've done, magnetic field of solenoid, we've done already, magnetic field outside of a toroid, I didn't bother. Displacement current, Gauss's law of magnetism, Ampere's law with correction. All right. There's still homework problems from chapter 31. You want to throw the chapter 31 quiz up next week also, or 2 weeks from now? How do you want to stack it up? Is it next week?
Sure.
Yeah, because the master said it's together.
So the homework quiz on 30 next week, the master set on 30 the following Thursday. And so I guess the homework quiz on 30 and 31. And no master set for 31. Cool. But I'm sure if you would like, I could whip one together and there'd be no mistakes, of course, because I throw things together at the last minute. That always works well. Not here in the groundswell for it. I will deny you a master set for chapter 31. All right, chapter 32, we get into the last piece. Faraday was playing around with the battery. So he had some sort of power supply here, positive and negative leads, hooked to a wire with a switch. Why he was doing it this way, I don't know. I've always sort of read it as he discovered it accidentally and then ran with it. Beside there, he had another loop of wire. They connected to it, he had what we call an ammeter, what at the time called galvanometer. There's a subtle distinction between the two, but they both measure current.